Conformations of organic molecules. Organic molecules can adopt different three-dimensional arrangements called conformations through rotation about carbon-carbon single bond. Understanding these conformational behaviors is going to be very important for us to predict the structure and reactivity of organic compounds. Chemists commonly use a visual tool called a Newman projection formula in order to represent the three-dimensional structures that is resulting from the rotation about the carbon-carbon single bond. A Newman projection imagines the viewer looking directly along the carbon-carbon bond axis. The front carbon is generally depicted as a point, while the back carbon is shown as a circle. And all the three lines that's coming from each of these carbons is going to represent the three bonds that's attached to that carbon. The simplest example is the ethane molecule, which can exist in a staggered conformation or eclipsed conformation. What's the main difference between the staggered conformation and the eclipsed conformation? In the staggered conformation, all of these hydrogens, all of these groups that is attached to the carbon are going to be away from each other. Whereas in the eclipsed conformation, they are going to be closer to each other. And we could clearly see the hydrogens that are attached to the front carbons are eclipsing the hydrogens that are attached to the back carbon. And we can convert the staggered conformation into an eclipsed conformation by rotating about the carbon-carbon single bond to an angle of 60 degrees. In general, the staggered conformation is more stable than the eclipsed conformation, and the energy difference between this is going to be 12 kilojoules per mole. What is the reason why the staggered conformation is more stable than the eclipsed conformation of ethane? This is due to favorable hyperconjugative interactions in the staggered arrangement, where the carbon-hydrogen bonding orbitals can overlap with the carbon-hydrogen antibonding orbitals on the adjacent carbon. We all know that hyperconjugation is stabilization effect, which is brought by the movement of the electrons from the filled atomic orbital to the empty orbital. And that's exactly what is happening here. So electrons from here are going to move on to the empty orbital. But such interactions are not happening here. We don't see any kind of hyperconjugative interactions happening here in the eclipsed conformation. And therefore, we can clearly say that the staggered conformation is more stable. Despite the stability difference, the ethane molecule is going to rapidly interconvert between staggered conformation and eclipsed conformation and all other intermediate conformations at room temperature millions of times per second. As a result of this, the individual conformations cannot be isolated, and the staggered conformation is the one that will be predominantly seen at equilibrium. Here is a graph that shows the different conformations of ethane molecule as you rotate about the carbon-carbon single bond to an angle of 60 degrees every single time. Let's start from this eclipsed conformer. Now, what we are going to do here is we are going to keep the first carbon, the front carbon, constant, and we are going to rotate only the back carbon. So which means as we rotate to 60 degree, what's going to happen to this hydrogen is it's going to come here, which means it's going to have the staggered conformation. It's going to assume the staggered conformation. And then when we rotate to another 60 degrees, this hydrogen is going to be behind the hydrogen that is in the front carbon. Right, so it's going to be eclipsed again, and then when we rotate another 60 degree, this is going to be staggered, and then another 60 degree that will be eclipsed, and then staggered, and then finally eclipsed. So this structure that we are seeing right here is exactly the same structure or same conformer that we started with in the very beginning. And we can see that there are totally 3 staggered conformations and there are 3 eclipsed conformations, and all these eclipsed conformations are different from each other, and similarly these 3 staggered conformations are different from each other, although we have exactly the same kind of atoms attached to both of these carbons. Larger molecules like butane have multiple rotatable carbon-carbon single bonds. Like all of these bonds can be rotated, and therefore they are going to lead to a variety of possible conformations. Now what we are going to do here is we are going to draw the Newman projection formula that you'll be getting both in the staggered conformation and the eclipsed conformation as you rotate about the carbon 1 and carbon 2 single bond. And then we are going to do the same thing for carbon 2 and carbon 3 single bond. So let's first draw the 2 Newman projection formula, both eclipsed and staggered conformation as you rotate about the carbon-carbon single bond from 1 to 2. Okay, so for which we are going to treat this as the front carbon, so this has to be represented as a dot, and this as the back carbon, so this should be represented as a circle. So we'll use different colors here. So the front carbon, this is our front carbon, so this is going to be carbon number 1, Let's put C1, and then we should have 3 bonds coming out of it. So these are my 3 bonds coming out of it. And all of these 3 bonds are attached, three bonds are towards hydrogens. So let's put the 3 hydrogens. Now on the back carbon, on the second carbon, I do have 2 hydrogens, and this is going to be an entire ethyl group. Right? So I can choose to start from the eclipsed conformation or staggered conformation. It's up to you, whichever you want to start from. But I wanted to use a different color here. So now I wanted to represent the second carbon as a circle. So and we could call this as C2. And we have to place 3 bonds. So this is my first bond, and this is my second bond, and this is my third bond. Okay, just be consistent with the position of these bonds. If you choose to put this bond after the blue bond, then make sure that every time you do the bonds, make sure that it is after the blue line. Okay, so just to be consistent. So it's attached to 2 hydrogens and also an ethyl group. So let's put the hydrogen here, and this is going to be our ethyl group. Okay, so this is the eclipsed conformation of butane molecule as we rotate about the carbon 1, carbon 2 single bond. Again, this is one of the conformations. You can have more eclipsed conformations as you keep rotating about the carbon-carbon single bond through 60 degrees. Now, if I'm going to rotate about this bond to 60 degrees, what's going to happen is this hydrogen is going to come here, which means it's going to be in the staggered position. All of these groups that is attached to the back carbon and the front, with respect to the front carbon, is going to be in the staggered position. So let's draw this again. So we'll represent the first carbon, the front carbon, as a dot, and then we should have 3 bonds coming out of it, and we are going to keep all of these bonds and the carbon constant. We're only going to rotate this. So nothing has changed on the first carbon, and now we are going to draw the second carbon, and now this is going to be staggered conformation. We have to make sure that we draw the bonds separated from each other, away from each other. And then we are going to shift this hydrogen here. This hydrogen is going to come here, and this ethyl group is going to come here. So it's going to be H, H, CH2, CH3. So this would be the staggered conformation. When we rotate about the carbon 2, carbon 3 single bond, we'll have different eclipsed and staggered conformations for this butane molecule. Let's at least draw one of the eclipsed and one of the staggered conformations that you'll be seeing in butane by rotating about the carbon 2, carbon 3 single bond. So we're going to take this as the front carbon and this as the back carbon. Okay, so we are going to represent the second carbon as a dot. So this is going to be C2, and then we should have 3 bonds coming out of it. And what are the groups that is attached to this carbon? So we have 2 hydrogens and a methyl group. I'm going to start with a conformer that is least stable, where I'm going to put the 2 bulky groups in the eclipsed position. So the bulky group that's present on this carbon is methyl group, right? So I'm going to put that in the very top, and then I'm going to put the 2 hydrogens on the remaining 2 bonds. Now this carbon should be represented as a circle. So let's draw a circle, and we are going to put the bulky group just adjacent to this methyl group to get the least stable conformer. So on this carbon we have 2 hydrogens and a methyl group, right? So the bulky group is methyl group. So let's put the methyl group here, and the 2 hydrogens on the 2 remaining bonds. Now this is the eclipsed conformation. Now as we rotate it to 60 degrees, what's going to happen is this methyl group is going to come here, and this hydrogen is going to come here, and this hydrogen will be moving in this direction. So let's draw the staggered conformation. So this is my front carbon again, which is C2, and this one right here is going to be my back carbon, which should be C3. Okay, and then I'll put 3 bonds. There has nothing that has changed in the front carbon. I still have the CH3, H, and H. Let's put those 3 groups here. Now this CH3 has come here in the staggered conformation. And then this hydrogen has come here, and the other hydrogen has also moved from its place. So this is going to be the staggered conformation. And again, these are not the only staggered or eclipsed conformation in butane. There are going to be other eclipsed and staggered conformation, which we will be seeing in the next slide. Okay, so here is the graph that's going to give us the different conformations, different staggered and eclipsed conformations of butane as you rotate about the carbon-2, carbon-3 single bond. Now, we started with the eclipsed conformation. Now, when you rotate it to 60 degrees, what you got was the 2 methyl groups adjacent to each other. Now, as you keep rotating to another 60 degrees, this is going to be giving the eclipsed conformation, and then again staggered, eclipsed, staggered, and then finally eclipsed. Now, this structure that you started with, this conformation that you started in the very beginning, right? This and this are one and the same. Okay, they're going to have the highest energy here because the 2 bulky groups are closer to each other, because of which there is going to be steric repulsion between the electron clouds of these 2 groups. So this conformer A, which is the eclipsed conformer, is going to have the highest energy. Now, which one is going to have the lowest energy? If the 2 methyl groups are going to be in the opposite direction in the staggered conformation, then that's the one that's going to have the lowest energy. And we are going to call this with a special name, call this anti. So this conformer D is called as the anti, which is going to have the lowest energy. So this one right here is going to have the lowest energy, D. And we also have 2 other conformers which are slightly higher in energy compared to D. And those are our gauche conformers. So we have B and we have F, which are also staggered conformations, but these staggered conformations are going to have slightly more energy compared to that of anti. They're going to have exactly the same energy. So B and F, they're going to have exactly the same energy. And here is B and F. This one right here is D. And then the remaining ones that we have here is C and E. Both are eclipsed. Eclipsed are going to generally have higher energy compared to the staggered, because you can see like all these staggered conformations are at the bottom, whereas the eclipsed conformations are on the top. So C and E should have exactly the same energy because they have about the same, the way the different groups are positioned on these 2 conformers are about the same, right? So C and E, they have exactly the same energy. So while we call this is the one that's highly unstable or the one with high energy, okay, this is the one that's going to have the lowest energy. And therefore, this is the one that's going to be more stable. And this is the one that's less stable. And we are going to call structures B and F as gauche conformation. So this is gauche, this is gauche. Gauche conformation is a staggered conformation where the 2 methyl groups or 2 bulky groups are in the adjacent position with respect to each other. Whereas the anti-conformation is the one where the 2 methyl groups or the 2 bulky groups are in opposite directions. So to conclude, organic molecules are going to continuously interconvert between their many possible conformations. The molecules are going to assume the anti-conformation where the groups are going to be away from each other to minimize steric repulsion. Here is an example shown. This is the ball and stick model of decane, where we can again see that the molecule is actually, the carbon chain is actually existing in the staggered conformation to have minimized steric repulsion between the different substituents.